This is the Tepid Coder. In this video, I want to talk about binary searches and what functions C++ gives you to handle those out of the box. So, say we have a list of numbers that are sorted, something like 0, 1, 1 again, a 2, how about a 5, I like that about a 2, how about 7, 9, how about 11, whatever. Now, how many do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8 items. Okay. Now, normally, when we search through a list, we'd start at the beginning and go to the end. Say we want the number 7. We're looking for 7 in the list, see if it exists. And if it does exist, what index is it at? So what we might do is we might say, start here at the 0. Is that a 7? No. Is it 7? No. How about this? Nope, nope, nope. Yes. So how many steps was that? Well, this would be the first, and this would be the 6th. So it's 6 steps. Okay. We can do a little better than that. Since we know the list is sorted, what we can do is we can divide the list into chunks. We have 8 total, so we can start at the 4th, somewhere in the middle of the list. You'd imagine the middle of the list would be element 4, right? 4.5 would be the element between the two, but we're truncating. We can divide the list in half, and we can look at whether or not the value is greater than or less than the value we wanted. So if we wanted the 7, we divide the list in half, there's 8 nodes. Let's start at element 4, half of that. Okay, so we're at 2 right now. Is 2 less than, or is it greater than the number we want? Well, 2 is less than 7, so that means it's going to be to the right of us since we're sorted in ascending order. So in that case, last time we added half of 8, this time we'll add half of the index we're currently on. I shouldn't say index we're on, but half of the element number we're currently on. So if we added 4 last time because it was half of 8, this time we're going to add 2 because it was half of 4. So we're going to go 1, 2, went up on the 6 here, and that is our 7. So we found it in 2 steps. That's much better than 6 steps. And I guess if we started from right and went to left, it'd be 1, 2, 3 steps. So binary search there is winning, just dividing the list in half. Now how about we want something like, I don't know, 1. Well, there's more than one to find. Either one would work. Either one of the ones. Kind of funny to say. Anyway, we'll start with the 2 again. So we have a list of 8 elements. We divide by 2 to get element 4. Okay. Then we're going to go left because 1 is less than 2. It's going to go left by 1, 2. Okay. And we're going to land on this 1. So again, 2 steps. And if I started on the left and went right, it'd be 1, 2 steps as well. Started on the right and went left, it'd be, 1, 2, 3, 4, 5, 6 steps. Actually, it'd be 5, and I'd hit this one instead. Either way. Trying to think here for a second. This can be slower for the extremities. The list elements on the left and right of the list, you'd have to start in the middle and kind of hop to them until you got there. So let's say I wanted to look for the number 0. I would start at 2 again, because we have 8 items. Half of 8 is 4. And we're going to say 0 is less than 2, so we're going this way. Right? Going to the left. And we're going to the left by 4 over 2, which is 2. So we end up here. And now 0 is less than 1, so we're going to left again. Before we went left 2, this time we're going to left 1 by 1, because half of 2 is 1. And now we're on the 0. So what did we hit? 1, 2, 3 steps for the 0. Versus just 1 step if we started here. Okay, how we want 11? Let's do the same thing. We're going to say we have 8 elements. Half of that's going to be 4. Alright, and then we're going to go to the right because 11 is greater than 2. And we're going to the right by 4 over 2. Okay, now we have 7 is less than 11, so we're still going to the right. But half of 2 now is 1, so we're going up here. 9 is still less than 11, so we should go to the right again, but half of 1 is going to be 0 when you truncate. So what we need to do in this case is if we haven't reached the end of the list yet and the current skip value is 1, we'll just have to move ahead 1 again. So there we go. We have 1, 2, 3, 4 steps to reach this 11, which is still better than 8 steps if I started here and just linear searched. So now there are certain functions we can use in C++ that will handle this operation for us if we don't want to write it ourselves. So we have something called, let's get some letters here. We have standard binary search. This will let us figure out whether or not a given value exists in a list. It won't tell us what index it's at, but it will tell us that it exists or not. We also have something called standard lower bound and standard upper bound. Now, you can use lower and upper bound to find the first element that isn't lower than some value you specify. So if I want to find, I don't know, let's say this 2 here, That's a bad example, because I mean I'll hit that first, but I'll go with it for now. In that case, it's going to do the same thing where it divides the list in half. It'll start here, and it's going to find the first value that isn't less than this number. Well, 2 isn't less than 2, so we'll just return this element right here, the next that element. Okay, upper bound is going to return the first value that is greater than that. Let's actually try and write these out real quick and just show that off. I'll use the same numbers too. So I'll show it in code. IO string I'm going to include, so I can do cout. I'm going to do algorithm, which is going to give me standard binary search. It's going to give me standard upper bound and standard lower bound. I'm going to include vector. I'm not going to use it right away, but I will get there in a second. So our entry point. Okay. Let's say we have just like number we're searching for. Constant I find me equals, how about 12? I'm going to do int ira values equals, give it some initial values, how about 0, 1, 1, 2, 5, 7, 9, 11 I think it was, okay. Let's say bool b exist equals standard binary search. We're going to search the whole range of this array, ira values up to array values plus, I'm going to say count of array values. Let's define that real quick. I'm going to say define count of a for array. We'll say it is the size of a for the array divided by its first element size. Okay, so you can imagine I have something like an array of ints. Well, its first element, I'll say right here, array values, position 0 is going to give me an int. So if this whole thing right here is int array, then ira values position in whatever, all but 0, is going to give me an int, right? That's the difference. So size of int array, what this whole thing is in bytes, divided by the size of each element in bytes, gives me the number of elements. So it'll give me 8. Okay, and then the value I'm actually searching for is going to be I find meat. And we're going to say standard cout, the value, whatever, I find meat, exists within the array. Okay. Now what I want to say is true or false for that. So let's actually drop this down. Okay. I'm going to say standard bool alpha. So instead of returning like 0, 1, it's going to return true or false in text. It's like true or false. So I'm going to say b exists, and let's try and build that real quick. Okay, 12 does not exist in the array. That is true. So let's pick a value that does exist. Let's do 11. It does exist, true, I found it. So that's cool. And this is binary searching list, which means it's starting here and it's jumping forward and jumping forward again and again. So it's really quick. Now, something else I want to show here is lower bound and upper bound. So let's look at lower bound first. And what I need to say about lower bound is typically it's used for standard template library containers. So if you have something like standard vector, so standard vector type int, instead of like an array of ints like this, then what it's going to want you to do is search the range begin up to standard vector int end, right? Or you could search less than that if you only want to search like the first half of the list or something. There might be a reason you're doing less, but it lets you do that. It's going to search this range right here. This is the sentinel here, so it's not actually checking that value. That's why I'm putting the parenthesis here. Anyway, I'm using just an integer array, which means it's treating it like an integer pointer for the start and an integer pointer for the end. So you can imagine this right here. We have int array being treated like int pointer, and right here we have like an int pointer plus some offset in memory, right? So plus number of elements in the array. So I also could have written this differently. I could say something like int pointer, let's say LPI, long pointed integer, I'll say sentinel equals, I could say ira values plus count of ira values. Right, so LPI sentinel, this will do the exact same thing. The other thing I could do as well is I could say reference the element right here. And the element right here is the first element past the end of the array. You can imagine, like, this is element 0, 1, 2, 3, 4, 5, 6, 7, right? That's index 7, but we have element 1 through 8. If we count like the first, second, third, fourth, fifth, sixth, right here, here's the 8th. So the last element has index 7, which is one less than the count. I'll be more explicit here, right? 8. Anyway, that being the case, if I'm referencing the count as the index, so element 8, there is no element 8. So it's the first invalid element in memory if I start at this address here in memory. So anyway, let's look at that real quick. I want to say I have int I, int LPI, I'll call it value. This pointer to value equals standard lower bound. And the range I'm searching is going to be iArray values up to LPI sentinel. And I'm searching for I find me. Now lower bound is not necessarily going to find the exact value I'm looking for. It's going to find the first value, which isn't less than the value I'm looking for. So finds the first value in the range of elements, not ranger, range of elements, which is not less than the value specified. Or it returns the sentinel if no such element can be found within the specified range. Okay. So standard cout, say, let me check what I'm searching for first. So I'm searching for 11, which does exist. Okay. Value. LPI value was found in the array. Okay. Let's use some checks though. So if LPI value points to LPI sentinel, then it couldn't find it in the range. So standard cout the value, in fact neither the value nor a value greater than, in fact neither, I'll just actually write the value out. I find me, nor a value greater, or a greater value I'll say, rather than a value greater than it, or a greater value could be found in the array. And then I want to return from here, return 0, let's say. Otherwise, that was the value that was found, which could be a value greater than the one we searched for, or the value itself. Okay. So the value 11 was found in the array. Cool. Let's search for a smaller value though. Let's search for 10 now. So in this case, the binary search isn't going to find the 10, but lower bound is going to find the 11, because it's the first value that isn't less than it. So let's show that. Okay, so 11 was found in the array, whereas 10 does not exist in the array. So it's a little nuance there. Now, there's a different thing we can do with upper bound. The upper bound is going to find the, geez, that was kind of annoying there. Let's try that again. Upper bound is going to find the first element, which is greater than the one I specify. Let's kind of label our test here real quick before I get this into a confusing state. So, testing binary search. Right, okay. Over here, say testing standard lower bound. Give this distance. Okay, and over here I'm going to say cout testing standard upper bound. Okay. Let's just steal this, I think. We'll edit as we need. So, in this case, we're going to say upper bound. This will return a reference to the first element, which is greater than the value specified, or it will return the sentinel if no such value, or actually no such element exists within the specified range. Okay. So in this case, if we're searching for something like 10, it's going to find 11. But if I search for 9, it's also going to find 11. So let's search for 9. So the binary search is going to say this exists. the lower bound's going to find it because it's not less than 9, but upper bound's going to find 11 because it's the first one that's greater than the one specified. So let's show that off. So come on, I'm going to have LPI value sentinel. So no value greater than whatever could be found in the specified range of elements. Yeah. Otherwise, we did find it. Cool. Okay, so here we can see it does exist in the array. Binary search found it, or at least found that it existed. Lower bound found that exact value instead of one greater than it, and upper bound found 11 because it was the first one that was greater than it. Now, I'm going to show an example of where these functions might actually be useful. It's going to be a bit of a contrived example, but we'll, work with it. So I'm going to say int, int test1 takes void. Okay, it'll return 1 with success, I guess. So let's make a vector. Standard vector int call it vec for vector equals some initializer list. I'm going to say 0, 1, 1, 2, 5. 7, 9, 11, same values. Now in this case I'm going to say I have a standard vector type integer iterator called it, which equals the lower bound of the range vec.again until vec.end. And I'm searching for, how about I find me, let's make that value again, constant I find me equals, let's say 10. So it's going to find 11. It's the first value that's not less than it. Okay. Now let's say I want to actually keep a vector full of values that are sorted in proper order while being able to binary search using standard binary search, standard lower bound, and standard upper bound for quick access to find things, while also allowing for multiple values of the same, actual value, right? It allows for duplicate values, essentially. So what I'll do in this case is I'm going to say something like, I want to insert the value that I'm looking for each time. And if I always insert before what it finds in lower bound, it should always insert it in the right place. So because I'm looking for 10, and I find an 11, I want to insert it before that 11. So I could say vec insert whatever it returns. So I'm going to say it, the iterator I found, and I'm inserting I find me. Let's actually show the list. I'm going to say for const auto reference, let's say I value from vec. Okay, we'll say standard cout value. Come on. I value. Okay, and we'll show that it inserts for that 9 and or sorry, for the 11, but after the 9. So okay, there you go. So 0, 1, 1, 2, 5, 7, 9, 10, 11. So insert between those two. Now it'll also work if it returns a sentinel, which is going to be, standard vector int end, right? If it returns the sentinel, it's still going to insert before the end, which is going to be the new last element. So let's search for 12. It's not going to find something that is greater than or equal to 12. So it's going to return end, and it's going to insert it before the end. So let's try that real quick. Okay, so you can see 0, 1, 1, 2, 5, 7, 9, 11, 12. So insert it after. So that'll work. Now if we want to make it so we can only insert values that already exist, there's 2 checks we need to do. So if we're making something like a set out of a vector, we could do this. If the iterator was returned equals vec end, then it doesn't already exist in the list. We're in the clear, right? So I'm going to say the value nor, so I'll say this, neither the value nor a value that is greater than it exists in the vector, not this, I'll say. So the value nor, instead of saying the value, I'm just going to say the actual value itself. I find me. After that, nor a greater value exists in the list, or the vector. Okay. In that case, I can insert it. So I'm going to say vec insert it. So if it's the end, doesn't matter. Like I said, it'll insert it over the last node. I find me is what I'm inserting. Okay. Otherwise, if it equals I find me, so I dereference it, and the value at that iterator is equal to the value we're looking for exactly, then the value already exists. So standard cout, the value already exists within the vector. In fact, instead of saying the value, I'm just going to say what it is. So it's going to be find me already exists in the vector. Okay. I'm going to make this a little bit different here. I'm going to say not equals, and I'm going to say no, I want to keep it that way. Yeah, and I'm going to do this, else. So if it doesn't already exist, then I can insert it. So the value, I'll say what it is. So I find me doesn't exist within the vector. However, a larger value does exist. Now, this is the case where it finds something like, say I'm searching for 10, it'll find the 11. So a larger value did exist. So lower bound returned something in that range, although it wasn't the value we were looking for. So in this case, I'm going to say I can also insert it. Let's do that, back insert. Otherwise, the exact value did exist in the vector already. Okay. So we're not going to insert unless we need to. So in this case, the value doesn't exist, and it's going to be after the 11, so it's going to insert it. Let's just test that real quick. Test that rather. Okay, here it is, 0, 1, 1, 2, 5, 7, 9, 11, 12. So it still exists. Let's try 11. It's going to complain that it already exists. Right? 11 already exists in the vector, so it didn't insert node 11. And then if we do 10, it doesn't exist, but it's going to find 11. Okay. 10 doesn't exist in the vector, however, a larger value does exist, which is 11. So insert 10 right here between the 9 and the 11. Okay. So, however, larger value, I'm going to see what that value is. Larger value, comma, whatever. Hold on a second. Do that. I want to say dereference the iterator to get that value to show it. I'm going to do this. Come on, really? I'll do this as well. Yeah, okay. Okay. So 10 doesn't exist within the vector, however, a larger value, 11, does exist. Cool. So that should allow us to insert however many elements we want into the list uniquely, if we really care about that. And the way I showed before is how you could just keep inserting values into the list while keeping the list sorted. So you can continue binary searching it and doing lower bound and upper bound on it. Anyway, if you found this useful, give the video a thumbs up and consider subscribing for more content like this. If you have any questions or suggestions or criticisms, please do post those. I have low enough volume that I'm able to read everything and respond to all the comments that I get, so I have been doing that. And I hope you guys have a great day. Thanks for watching. Catch you later.